Hello. Just forewarning, it's still very trafficy where I'm recording. You probably hear the car going by right now. That was fun. Um, so I apologize. On that note, hello, I'm Quillen. Welcome to Calculus. Today we're going to be once again continuing our discussion of trig limits using some algebraic properties. Today we're going to be talking about double angle identities. Now, I did not learn these in my pre-calculus course because my state does not require students to learn these in pre-calculus. So I had to self-study these and memorize them. There are only 5 to know, so it's not terribly difficult. Let me pause very quickly and I'll pull up the 5 that you need to know. All right, these right here are the 5 double angle identities that you need to know. And as you could have probably guessed, the double comes from the fact that the argument inside of your trig function is being multiplied by a coefficient of 2. And that A stands for argument. It might just be 2 theta, or it could be 4 theta, and then you have to sort of do it recursively. Or it could be something else entirely. Just remember this formula and remember your skills from algebra, and you'll be completely fine. The same is true for these other 4. I'm going to be doing my best to only use number 1, number 2, and number 5 because 3 and 4 can be derived algebraically from 2, and it's good practice to know your Pythagorean identities, and you can move back and forth between them. I think that going to this one is the easiest, though. All right. Let's do some examples of using these in your limits. Because a lot of people honestly do not even remember these exist by the time they get to calculus, because it's been a whole 2 to 3.5 months since they last even thought about math. So, our first example, I will write and then you come back. All right, here is your first example. It's a little bit small and I apologize. So I'll zoom in. So I want you to find the limit of the function 1 plus the square root of 2 times the sine of theta all over cosine of 2 of theta, of 2 times theta, rather, as theta approaches negative pi over 4. Well, thinking back, the first thing you're going to want to do is plug in negative pi over 4 because the numerator and the denominator are both continuous. That just means they have no holes or gaps or jumps or anything. If you traced your finger along it, you would never have to pick up your finger. If you were drawing it with a pencil, you would never have to pick up your pencil. So, think back to your unit circle. Sine of negative pi over 4. So that is in the 4th quadrant, meaning your sine is going to be negative square root of 2 over 2. And if you multiply that by the square root of 2, you're just going to get 1. Or you're going to get negative 1. So you have 1 plus negative 1, that's 0 on top. And then the cosine of twice that is going to be, so you're going to go to negative pi over 2. That's going to be negative 90 degrees. So your cosine is going to be 0 there because it's right on that y-axis. So you have your friend 0 over 0, our indeterminate form. So that means we can't really say anything about this with certainty because it could go to infinity, it could asymptote to 0, or it could do neither of those. So let's do our double angle identities. So this top, it's not going to change because that argument does not have a 2 in front of it. So our top stays the same. However, the denominator is going to change because its argument does have that 2 in front of it. But remember, it doesn't just have to be a 2. I think it works with any even number. Some people say it works with any number at all. It really just depends on your situation. So the traffic is real bad today. I didn't realize it was going to be like this. So your cosine of 2 theta, it's going to become cosine squared of theta minus sine squared of theta, just like it has over here. And remember to do the part that you think is going to be longer if you are picky about your denominator and numerator being centered with your fraction bar. Now, just like before, we are going to do difference of squares. But our difference of squares is going to leave us with a cosine part and a sine part in each of our parentheses. So let's look up here, and you'll notice, of course, that the only trig function in your entire numerator is this sine. So thinking back to your Pythagorean identities, cosine squared equals some other combination of functions. So pause for a moment and see if you can figure it out for yourself. All right, I hope that you found that cosine squared equals 1 minus sine squared. And if we go ahead and combine like terms, we will get this. The top's going to stay the same. So I'm just going to I'll write it out. There's no reason not to. The top's going to stay the same, but the bottom is going to become equal to 1 minus 2. Or it's not going to become equal to. It already is equal to 2 sine squared of theta. And right here, it should be square root of 2 sine theta, but you know that. So if you have already written this down, fix that in your notes. If not, no worries. Just make sure you write in that sign. Now, we can do difference of squares to the bottom. The top will still stay the same. It will still be 1 minus square root of 2, 1 plus square root of 2 theta, rather, because we're not doing anything to it. Square root of 2 sine theta. I keep saying it wrong. And that is messy, messy, messy. But you heard me say it out loud, so hopefully you know to write it in sine, not whatever that scribble scrabble is that I wrote. So your difference of squares is going to leave you with 1 plus square root of 2 sine theta. I almost forgot the square root. 1 plus square root of 2 sine theta times that same thing but with a minus sign. So 1 minus the square root of 2 times the sine of theta. And just to make sure you've been paying attention, this limit should carry out through each of these terms that I'm saying are equal, because technically there is one unequivalency that we get rid of when we cancel. So the limit is equal, but each step of the process isn't quite equal. Now, these cancel just like everything else we've been doing, leaving us with 1 over 1 minus square root of 2 sine theta. And as we discovered earlier, the sine of theta in this case is going to be negative. Sorry, my brain froze. It's going to be negative square root of 2 over 2. Multiplying that by the square root of 2, you're going to get 1. But this time, because it's being subtracted from 1, it's going to add. So 1 minus a negative, it's going to be positive. So that leaves us with our limit being 1/2. That's your final answer. Let's go check it in Desmos. Let's turn off this purple function. And let's also, I'm going to show you how to do this in case you don't already know. You can change the step by going to step right here and writing in whatever you want to write in for your step. And if we look at pi over 4, it does look like it's going to pass through 0.5 right there. So that means we got the right answer. Good for us. Now I will move on to your next example. I'll pause to write it out, and you can come back. Anyways, here's your next limit. I want you to find the limit of cosine of 2x over cosine of x minus the sine of x as x approaches pi over 4. So first thing you do, of course, check what this is. So the cosine of twice pi over 4 is going to be the same as the cosine of pi over 2, which, as we already discussed, is 0. And the cosine of x is going to be square root of 2 over 2 minus the sine of x is also going to be the square root of 2 over 2, because that's what's interesting about pi over 4 is the tangent equals 1 there. So that means we have our 0 over 0 because any number minus itself is 0. So now what we have to do is start doing some manipulation. Now, remember your double angle identities will tell you that cosine of 2x is the same as sine squared of x minus cosine squared of x. And that is the exact same as what we did up here. I got it backwards. So I'll just switch these signs around. So I made a tiny little ticky mistake like that because I was being careless. So make sure that you are paying very careful attention and using your past work to do your future work. That's always a good strategy. And then I'm going to get this in the right order. So it's cosine of x minus sine of x. And then from here, we can do some difference of squares. So we have cosine squared of x minus sine squared of x, which will leave us with cos x minus sine x times sine x, or times cosine x plus sine x. And for that one, I could have gotten them backwards because addition is commutative. And so the order for that one doesn't matter. All of that over cos x minus sine x. So these are going to cancel, leaving you with just cosine x plus sine x. And remember back here, we decided that these have square root of 2 over 2 and square root of 2 over 2 as their values, which means our answer is just going to be 2 times the square root of 2 over 2, which will simplify down to the square root of 2. Now, if we go to Desmos to check our answer, I've already messed with the steps to get us to pi over 4 and the square root of 2. This is just how Desmos approximates square root of 2. And if we zoom in on pi over 4 and the square root of 2, you will see that it does appear to have a vertex right there, which means our answer is correct. I hope that you have found this video helpful, and I also hope that you will continue with me on this journey through calculus. I hope to see you tomorrow. This is Quillen signing off.